Hello, everyone. Welcome again to the Shannon channel. Today, I'm really happy to have Yihong Wu from Yale, and he's going to talk about self-regularizing property of non-parametric ML estimator in mixture models. Welcome, Yihong. So we're all going to listen to you.
Thank you so much. Thank you for the invitation. Can you hear me well?
Yeah. Yes.
Okay. So I want to present some recent results about non-parametric MLE in mixture models, especially its optimization properties. So this is joint work with Yury Polyanskiy, and this is mostly a statistics talk, and there's some intersection with information theory, as you will see. All right, so let me give a quick spiel about mixture models. It's a very widely used methodology to model population with some heterogeneity. For instance, a population consists of a number of subpopulation. For instance, if you, so this is just a cartoon, I think, for the high distribution of a given population, and then it does not look like Gaussian, and in fact, it's a superposition of two subpopulations, let's say male and female, each of which is much better modeled by a Gaussian distribution. Right? And then, and the goal in mixture models is to model such situations with with a more complicated distribution, as opposed to a Gaussian with one component with multiple, and this can potentially fit data well and has more interpretability, right? Like corresponds to the hidden subpopulation. And the goal in mixture model is always the following: without knowing the label, right? Without knowing, let's say, a given sample is male or female, you want to learn the average height of the male and female population from unlabeled data. So the difficulty in mixture model is always due to the latent labels. All right, so let me give a mathematical setup of mixture model that we're going to consider in this talk. Very generically, you have a parametric families of distributions, for instance, a family of Gaussians where the parameter is a mean. And then let's call these parametric densities P sub theta, and capital theta is the space of parameters. And then pi throughout the talk denotes a distribution or prior over the distributions. And pi, when you average the parameters according to pi, you have now a mixture distribution, right? So mixing distribution is the distribution over the parameters. Mixture distribution is the induced, right, distribution over the observables, right? So you can think about p theta as a channel, if you will, and pi as the input, and p pi is the output. Yeah? So p pi is just the average density over the prior. And the special case is when pi is just a sum of k delta functions. So in this case, the mixtures is just a superposition of a weighted convex combination of three distributions with different parameters. Right? So this is usually referred to as finite mixtures, but we're not going to constrain ourselves on finite mixtures only. Okay, so and the goal in mixture model is that given data x1 to xn drawn, for instance, independently from some mixture model, p pi, and you want to learn either the mixing distribution pi or learn the mixture density p pi. And then, so this is, and without knowing, right, you can think about there's some hidden theta 1 to theta n that generates these, and these are latent, right? So these are not observed. So these are not observed. Okay. The running example I will consider throughout the talk is the simplest possible situation, which is a Gaussian location model, where p theta is the density of normal theta comma 1. Right? So it's just a shifted normal centered at theta with standard deviation 1. And in this case, in the Gaussian location mixture case, p theta is nothing more than just a convolution of the mixing distribution convolve with the normal density, right? Normal density throughout the talk is denoted by phi. Okay, but the results that I'm going to present is not confined to Gaussian distributions only. Any questions about the setup? If not, I will continue. Okay. And the most prominent difficulty in mixture model is, of course, its non-convexity. So for instance, if you have a finite mixture model, let's say 3 components, the likelihood in terms of the weights is, of course, convex, like concave, right? Maximizing concave, so that's easy. In terms of the location parameters, thetas, they are not. Right? So this is the usual difficulty in mixture models that makes, for instance, computing maximum likelihood difficult. Right? Indeed, recent results has shown that there exist spurious local maximas in the landscape of the likelihood function, even when you have infinite number of samples. Therefore, heuristics like expectation maximization, which is the iterative algorithm, in certain cases reduces to gradient ascent for approximating the maximum likelihood estimator, could potentially get stuck at these spurious local maximas. Okay, so and as opposed to this type of more parametric approach, there is non-parametric approach that forgets the true mixture could potentially be have finite number of parameters and just treat the problem as an infinite dimensional problem. And the benefits is usually in terms of flexibility and in terms of computation. So let me mention a few. So there are 3 major methodologies in the non-parametric learning of mixture models. Number 1 is method of moments. So I regard this as a non-parametric approach because it's not tied to, it doesn't directly work with the individual parameters in defining a mixture distribution pi. So the principle is to learn this distribution by learning its moments, right? If you know enough information about its moment structures, you can reconstruct pi up to certain accuracies. So this is introduced by Pearson in 1895. And in one of the earliest papers in mixture models, where he used a mixture of 2 Gaussians to model population of 2 species of crabs. And then second prominent methodology that has a non-parametric flavor is the minimum distance estimator, introduced by Wolfowitz in the 50s. And the rationale is the following. I have empirical distribution of my data. I know they're distributed according to some mixture distribution with some true mixing distribution pi. So let me try to estimate it, pi, by fitting the best p pi in some reasonable distance to the empirical. Okay, and then I try to solve this minimization over O pi, and this is usually done in a non-parametric way. I want to minimize this convex function over a class of measures. So this is highly useful in learning mixture models. And the third approach, which is the one that I will focus on today, is to compute maximum likelihood over infinite dimensional space. And then this approach is introduced by Kiefer and Wolfowitz also in the 50s. And this has become one of the methods of choice in learning mixture models, especially its applications in empirical base, that hopefully I will have some time to discuss. All right, so this is the quantity I want to focus on today. Right, so still, we're going to take the route of maximum likelihood, but I'm going to relax my decision variable to the space of all distributions. So so this is, as a shorthand, I will call this NPMLE, a non-parametric maximum likelihood estimator, and which aims at optimizing the likelihood over the entire space of distributions. Right. So I have some parameter space theta, and let me denote script m as the collection of all distributions over theta. Right. So, and then I have n data points. So I compute the total likelihood, right? So the average log likelihood over these m observations, and I maximize this over all priors, right? So so even if I know the true component has a finite number of components, I run this infinite dimensional maximization. So what is the benefits? Clearly, the most immediate one is that it convexifies the problem, right? The feasible set is now a convex set, and the objective function is concave. So this is a convex optimization problem, but doesn't mean it's easy to solve because it's infinite dimensional, right? Unfortunately, in one-dimensional models, in other words, theta, the set theta is a subset of the real line, and this can be efficiently solved in many different ways. And the basic property of this strategy, of this estimator, for instance, the existence and the uniqueness of the solution, and also that the solution will turn out to be a discrete measure, right? Even if you solve this maximum likelihood over infinite dimensional space, the solution will not have a density. The solution will be a discrete measure. And these basic properties has been well understood. So the first result along this line was due to Simar in the 70s on the Poisson mixture model. And then Joel extended to exponentials. And Lindsay has a general treatment for all exponential families, including Gaussians. So a very good reference along this line is his 95 monograph on mixture models that is still, has become a classics in this field. So as I said, this infinite dimensional convex optimization problem, at least in one dimensions, can be resolved very computationally efficiently using different methods. So there are iterative algorithms has been proposed over the years. And also more recently, people start to use more grid-based, let's discretize the set into 3,000 bins and just run your CVX on top of that. So they also performs very well. So in other words, so this convexification from the set of, let's say, finite mixtures to infinite mixtures does not pose any computational issue. Actually, it resolves the non-convexity that I mentioned in the beginning. Okay, so let me summarize the main benefits of. Yes, please. Yes.
I'm assuming n is the number of samples, right?
Yes.
And how does it affect this as an optimization problem? How does it affect it? It just
right. So for instance, some of the properties of the solution will be related to the sample size. So it is known that if you have n observations, the solution is a discrete one with at most n atoms.
Okay.
So this is known, and then the solution, the main results we're going to present today will improve along these lines.
And by one-dimensional, you mean n equal to 1, or?
No. Sorry about that. It's by which I meant then this set is a subset of R.
Okay.
So for instance, a mixture of Gaussians in one dimension.
Okay.
So thanks for the clarification. If n, so let's continue with the summary of the benefits of this non-parametric maximum likelihood. So I think the most prominent and the most important advantage is that it's extremely flexible, right? So as I said, it does not postulate. So can you guys still see me? My computer went black.
Yeah, we can see you and we can hear you also.
Okay, so maybe let me just continue.
Yeah, we see you.
If somehow, so my computer sometimes has this problem. Okay, so let me continue. So the most important advantage is that it is extremely flexible. It does not have any tuning parameters, right? It has no penalty parameters. So there's no use for choosing any penalty parameters, and does not assume any upper bound on the number of components in the true population, right? Because here I have extended my model to infinite mixtures. So, and this is extremely useful in practice because it's very annoying to try to estimate how many components there are in the true population. So it would be very advantageous to assume nothing, right? And secondly, is for computational considerations. And such approach is solve the convexified problem, a relaxed version. It does not suffer from non-convexity in the usual finite mixture model. And the third thing is it retains the accuracy still. So it achieves a near parametric rate in the sense of it only is worse than a finite number of than the models with finite number of parameters by a possibly polylog factor. Okay. And due to its flexibility, it has been widely used in empirical Bayes estimation, and it achieves superior performance in both theoretical and practical sense. Okay. So the potential issue with this strategy is that, as you can see, that it can be viewed as extreme form of overparameterization, right? So even if the true population is known to have at most 4 components, I relax it into an infinite number of components, overparameterize my model in order to convexify the problem, right? So therefore, it's potentially can overfit the data. But probably, as you have heard in more recent years, results from machine learning has told us that overparameterization does not necessarily lead to overfitting. So this work aims to explain this effect in the context of mixture models. So the major question that I want to address is that does non-parametric maximum likelihood actually overfit, right? If the data is drawn from a small mixture. So most specifically, suppose you're given data generated from what I call a KGM, in other words, a k-component Gaussian mixture, let's say with 2 components. What is the typical model size fitted by the non-parametric maximum likelihood? Because after all, it's trying to fit an infinite number of components, right? Does it actually somehow magically fits appropriate small model?
Yihong, I think the slides, Zhang has notified me that, and he said on the chat that the slides are not moving. Well, now they're moving, so.
Oh, okay. So.
Ask him, so is everyone saw the slides moving?
Strange.
No, he's saying now it's good, so it's good now.
Oh, okay. Good. Oh, thank you so much.
Yeah.
Yeah, I have no idea why. Right. So as I said, the major question that motivates this research is that as people observe in practice, this overparameterization actually does not hurt that much. The model fitted by this infinite dimensional model usually is a very reasonable sized small mixture. And we're trying to answer or explain this phenomena. And it turns out that these questions are not explained by classical theory. So some new thoughts has to be needed here. Okay, so let me give you a review about the classical results about the structures of this optimization problem. For instance, I mentioned earlier that this is known to be a discrete measure whose number of points is the most sample size. So let me explain this. Okay, so first of all, let me recall the objective function is the average log likelihood, right? So average at the sample point, and let's denote the maximizer by pi hat. So we know that from the optimality of pi hat, any perturbation of pi hat can only beat it, right, in terms of the objective function. So therefore, if I choose my favorite point, if I add 1 more atoms to my proposed solution, right, and take linear wave convex combination, this can only make the likelihood worse. So therefore, this immediately leads to the first order condition of the derivative along this perturbation, right? Along the direction of a point mass at the proposed maximizer to be non-positive. So this is the usual thing. And these are, right, from the surface, necessary conditions for optimality. But because the problem is convex, this is sufficient as well, right? So you can prove easily, just thanks to concavity of the objective, whenever you have this guarantee, this first order condition ensures optimality as well. So let me summarize. So if I call this d theta, right? So this derivative at perturbation along the point mass theta, and this of course depend on theta pi hat, right? So this pi hat, and then if you just take the derivative over this log likelihood, it's very simple. It's just the ratio of the I sample at p theta over the fitted likelihood, right? The fitted likelihood. So the optimality of a solution pi hat is equivalent to the fact that this derivative d theta is pointwise upper bounded by theta everywhere. So this is actually a necessary and sufficient condition for optimality. And this is the basis for not just our results, but also the classical understanding about this optimization too. Okay, so the consequence of this is that it tells you a lot of information about the solution. Although this cannot be taken as an immediate solver for the pi hat, because pi hat enters the denominator also, right? So with the relationship of pi hat to the derivative is the following: if you average the derivative over pi hat, right? Average this d theta when you draw theta from pi hat, and this is exactly equal to 1. Why? Because averaging p theta over theta according to pi hat exactly cancel the denominator, just with the definition. So you have a situation of a function, of some function, which is pointwise upper bounded by 1. And when you average according to some distribution, you exactly hit the upper bound. So this tells you that this measure that you are averaging over must be supported on its global maxima, and the global maxima is equal to 1. Right? So this is a picture of theta versus d theta. So therefore, the consequence is that the support of this solution is contained in the global maximizer of the derivative evaluated at the solution. So it's a tail biting condition. And also it's further included in the local maxima, and therefore it's further included in the set of critical points. Okay. So therefore, if I can show that a function of this form, of this form, can only have finite number of critical points, it will imply any solution must be discrete. So that's the rationale that that was observed. That was the observation was first done by Simar in the context of Poisson mixtures. So let me explain this just in the context of Gaussian mixtures, because this is our running example. So in the mixture of Gaussians, this p theta is just a shifted normal, right? And this is some fitted likelihood, which is hard to describe, right? Because this is determined by the optimal solution. But nevertheless, the form of this derivative, this gradient, is clear, right? It's a convex combination. It's proportional to a convex combination of a bunch of Gaussians centered at the data points. Right? In other words, this gradient is proportional to the density of a Gaussian mixture with n components, right? With center at x1, x2, up to xn. So if you have 100 samples, the gradient is exactly of the form of Gaussian mixture with 100 components. And it is known a long time ago that if you have convex combination of Gaussians with n components, if you take a superposition of n Gaussians in one dimensions with different centers, in fact, with different standard deviation works too, this can create at most n local maxima. So this can be proved in various different methods. One way is just to analyze how many solutions can the gradient have. Okay, so this implies that the solution is going to be at most n atomic. Right? So because regardless of the choice of this part, which is hard to describe, and nevertheless you cannot create more than n modes. And then if you can show the solution is unique, exists and is unique, right? So because this part hinges on the fact that there exists some pi hat, so maybe it doesn't exist. So first you prove it exists, then you prove it's unique, then it has this structure property, right? It's not only it's a discrete measure, it's a discrete measure with at most n atoms. Okay, so this is known for a long time now, but it does not answer the question that I want to address in the beginning. Right? Suppose I have 100 samples. This result only tells me that I will not fit more than 100 components. But if you actually fit 100 components, kind of destroy the purpose of the mixture models, right? So it sounds very much like you're overfitting. You would like to fit a small mixture model, explain these 100 data points you collected, right? Rather than attribute, for instance, each data point to a single new cluster. So that's kind of it's right. It sounds very much like overfitting. So this results is highly useful, but it does not resolve the question, this more precise question that I want to answer. So it turns out that this determinant, yeah, there was a question.
It's, can I add just a regularization term, or is that something
right? So very, very good point. So, so I will come back to this later on. So you can try to, and this is usually the point of adding a regularization term or a penalty term. Try to penalize more complex model, encourage simpler model. So one way people do is that, like in model selection, you try to fit a model the growing size, but then you add a penalty term that subtract some term, penalize for more complicated model. And this makes the problem computationally difficult because you have to solve, you have to fit mixture model with 10 components, 11 components, 12 components, so on and so forth. And this runs into the problem of non-convexity. So the solution, the results that I want to mention, which we call self-regularization, is that without any regularization term, it automatically regularizes itself. So this is probably the surprising results of this work. And I'll come back to this penalized, this regularized version, I think maybe in a few slides. But let me mention that this pessimistic results is actually tight in the worst case. So I can cook up samples, which I will do on the next slide, that if you have 100 sample, you will indeed fit 100 component mixtures. So there's no way to improve over this deterministic result because it's tight in the worst case. But in practice, model fitted by NPMLE has a much simpler structure, has much less component than predicted by the worst case guarantee. So of course, the question is, can you improve the results for random data? Right? If the data are generally drawn from some distribution, for instance, the mixture, actual mixture distribution, can you improve over this worst case analysis? Right? Can you say something more about the number of components in the worst case? So let me give you two examples, two computational examples. where I feed the optimization with different style of sample. And the first one is the data points are extremely spread out, in the sense of it's just starts from -15 to +15 with the increment of 3. Right? In other words, you have data points, right, plotted here in these red dots that are separated by 3 times the standard deviation. And I insist ask you to fit a mixture of Gaussians with 1 standard deviation. So if you run the program, and the results will be actually 11 component. So you will fit. So this blue is the fitted density. So indeed, it has 11 components, and the mode of this fitted mixture is very close to the observation that you'll see. So this actually, it somehow makes, I mean, in some sense, it's very reasonable. If somehow the data is so spread out, and you're tasked to fit a Gaussian mixture that best explain this, the best explanation is probably just to say each data point form its own cluster. Right? So so this is known before, that if you have data of this form, it will fit a huge cluster and a huge mixture model. So this is a bad news, right? So this can actually happen. So this worst case happens essentially with positive probability. But the good news is that this sample is an atypical configuration. If your data is truly drawn from some mixture models, let's say IID, the fact you observe these well spaced out situations is very unlikely, right? It can happen with some positive but low probability. So